First of all, I would like to thank the conference organizer for the introduction. Good day, my name is Voon and I'm from Institute of Nanoelectronic Engineering, University Malaysia Perlis, Malaysia. I want to express my gratitude to the conference organizer for inviting me to present my work. Without further ado, I would like to start my presentation. The title of my presentation today is Welding of Thermoplastic Using Silicon Carbide Nanomaterials as Susceptor by Microwave Heating. Here's the outline of my presentation. I will start my presentation with an introduction to microwave welding and heating. Then I will discuss the motivation behind this research. Following that, I will discuss briefly the methodology involved in conducting this research. And next, I will present the findings in this research and I will end my presentation with a conclusion. So first of all, what is welding? So welding is a joining process in which metals or sometimes plastic are heated, melted, and mixed to produce a joint with properties similar to those of the materials being joined. There are several types of conventional welding, which include hot tools welding, friction welding, ultrasonic welding, and laser welding. However, these methods have drawbacks, such as geometric restrictions, the inability to be applied to large joining areas, and the requirement for a scale operator. Microwave welding is a relatively new joining process that uses microwave heating and a susceptor to combine two or more individual pieces into a bigger and complicated component. Microwave welding offers a controllable heating rate and can be applied to joining areas of complex geometry. It also ensures a high level of safety and is environmentally friendly. Moreover, it provides ease of disassembly and can be easily scaled up for larger applications. So let's talk about the microwave heating. Unlike conventional heating, which relies on heat conduction, heat radiation from the surface to the center of the material, microwave heating works differently. As shown in the figure on your right, microwave heating involves the absorption and conversion of microwave energy by a susceptor, resulting in what we call volumetric heating. This means that microwave penetrate uniformly throughout the entire volume of the material, delivering energy evenly and efficiently. Therefore, microwave heating offers rapid processing, uniform heating, and minimized temperature gradients across the material, and it is a far more superior method compared to traditional heating techniques. However, not all materials can be heated effectively when exposed to microwave irradiation. Based on their interaction with microwaves, materials can be categorized into three types: microwave absorbers, refractors, and materials that are transparent to microwaves. Only microwave absorbers can effectively absorb microwave energy and convert it into heat. So, when welding materials that are refractors or transparent to microwaves, we rely on susceptor to facilitate the process. A susceptor is a material that absorbs microwave energy and converts it to heat. During microwave welding, susceptors are used to absorb microwaves and convert them into heat. The heat is then transferred to the neighboring joining surface, causing the susceptor to become embedded in the molten layer under pressure, and a welded joint is formed as the joint cools. Therefore, a susceptor is one of the most important components for a good welded joint. Currently available susceptors include carbon-based materials and conductive polymers. Carbon-based materials are excellent susceptor due to the presence of delocalized sp2 electrons. However, they have low magnetic loss, making impedance matching difficult, and they pose health hazards. Conductive polymers, on the other hand, require additional processing to introduce free electrons before they can be used as effective microwave susceptors. Therefore, there is a need for a more effective susceptor. Electromagnetic waves, such as microwaves, consist of alternating electric and magnetic fields. Silicon carbide can effectively absorb microwaves due to its unique dielectric properties and the covalent bonding between silicon and carbon atoms. The difference in electronegativity between silicon and carbon results in a degree of charge separation within the bond, creating localized dipoles. While these dipoles are not permanent, they can interact with alternating electric field of microwaves. The dielectric properties of silicon carbide also enable it to polarize in response to the electric field and results in dielectric heating, where the material absorbs microwave energy and converts it into thermal energy. Therefore, silicon carbide is an excellent material for microwave heating applications. In this study, we propose using silicon carbide nanoviscors as a susceptor material. Silicon carbide nanoviscors are a dielectric material with high electromagnetic absorption, thermal stability, and mechanical strength. Their one-dimensional structure and high specific surface area further enhances their microwave absorption capabilities, making them ideal for this purpose. Here's how we prepare our welded joint samples. First, we created a suspension of silicon carbide nanoviscors in acetone by dispersing silicon carbide nanoviscors powder into acetone using magnetic stirring, followed by ultrasonication. This suspension was then applied to polypropylene substrates via drop casting, followed by drying. Next, a second PP substrate was placed on top of the silicon carbide nanoviscors coated PP substrate, and a coupled substrate was subjected to clamping pressure using a domestic microwave oven. We applied heat to weld the samples together. Through this process, we form welded joints by clamping and irradiating the substrates. Our investigation also examined the impact of various parameters on the welding process to achieve optimal conditions. Here is the silicon carbide nanoviscors reinforced PP welded joints are formed by microwave welding. Initially, the coupled substrates were subjected to microwave irradiation during the microwave process. Prior to irradiation, the silicon carbide nanoviscors were positioned at the interface between the two PP substrates. During microwave heating, the silicon carbide nanoviscors absorb microwaves and convert them into heat. This heat was then transferred to the adjacent PP substrate interfaces, causing them to melt. Simultaneously, under the applied pressure, the silicon carbide nanoviscors penetrate into the molten PP interface, and after cooling, a silicon carbide nanoviscors reinforced PP nanocomposite is formed at the interface. In the first part, we employ a silicon carbide nanoviscous suspension as the microwave susceptor. This susceptor offers the advantage of easy application to components of any geometry without requiring additional processing steps. In our study, silicon carbide nanoviscors not only function as a subceptor for microwave heating, but also serve as a filler to form a nanocomposite in the welded joint. We studied the effect of various parameters on the welding, and this helped us optimize the conditions for the best mechanical properties. Here, we investigate the impact of microwave heating duration on the mechanical properties and microstructure of welded joints. The duration of microwave heating significantly affects the fracture strength and modulus of elasticity, with values increasing up to 18 seconds, after which they decrease. Conversely, flexural strength decreases with prolonged heating. The improvement in fracture strength and modulus of elasticity correspond with the average thickness of the welded joint layer. For instance, as heating duration increases from 10 to 18 seconds, the average thickness rises from approximately 150 microns to 180 microns. The average thickness rises from almost 20%. This increase is due to the enhanced heat release from silicon carbide nanoviscors during longer duration, facilitating deeper PP interface melting and thicker molten layer formation. Deeper silicon carbide nanoviscors embedding within the PP interface restrict the PP chain mobility and therefore promoting a thicker silicon carbide nanoviscors reinforcement PP nanocomposite at the joint, thereby enhancing their mechanical properties. However, while the high modulus silicon carbide nanoviscors improve stiffness, they constrain the PP chain mobility under stress, and therefore reducing the flexural strength. Notably, at 20 seconds, the average thickness drops to 125 microns, and SEM images show non-uniformity with observable voids throughout the joint layer. And this inconsistency and reduced thickness at 20 seconds indicate excessive heating may volatilize the PP substrates and compromising the joint integrity. And therefore, identifying an optimal heating duration, here as the 18 seconds, is crucial for ensuring robust and durable joints. In addition to heating duration, the solid loading of silicon carbide nanoviscors in the suspension significantly influences the mechanical properties of the welded joints. We conducted experiments with varying solid loadings ranging from 7.5 weight% to 10 weight% to determine the optimal loading for maximizing the strength. Flexure strength and modulus of elasticity increase as the solid loading increased from 7.5 to 8.75 weight%, but decreased with further increments beyond 8.75 weight%. However, the flexural strength decreased consistently with increasing silicon carbide nanoviscous loading. The average thickness of the welded joint layer consistently increased with higher solid loadings. Incorporation of more silicon carbide nanoviscors into the PP substrate during microwave heating effectively restricted the PP chain mobility under stress and therefore resulting in a higher fracture strength and modulus of elasticity. However, the SEM image of joint formed with the 10 weight% solid loading revealed voids and silicon carbide nanoviscous agglomeration within the joint due to uneven dispersion. And these irregularities act as stress concentrators and thereby reducing the mechanical properties. Therefore, optimizing the solid loading of the susceptor is crucial to achieve well-formed welded joints with optimal performance. We also conducted a comprehensive study on the effect of microwave power on the mechanical properties and microstructure of welded joints. Microwave power significantly influences the heating rate and thus affects joint formation in our experiments. We can see that as the microwave power increases, both fracture strength and modulus of elasticity improve steadily, while the flexural strength decreases. Notably, at 18 watt, we fail to achieve a welded joint due to inadequate microwave energy absorption by the silicon carbide nanoviscous to melt the PP and form the joint. SEM images reveal a uniform welded joint layer thickness across all power settings. The average thickness of the welded joint layer increases with higher microwave power levels because the higher heating rate associated with increased power levels enables melting of a thicker PP substrate at the subinterface, resulting in a thicker welded joint. Additionally, deeper penetration of high modulus silicon nanoviscous into the PP matrix at higher power level enhances the fracture strength and modulus of elasticity. However, this also restricts the PP chain mobility under stress, leading to reduced flexural strength. In conclusion, based on our investigations, 800 watts emerged as the optimal microwave power setting for achieving welded joints with highest mechanical properties. We also investigated the effect of clamping pressure on the mechanical properties and microstructure of welded joints. We found that mechanical properties were markedly influenced by clamping pressure. Welded joints without clamping pressure, denoted as P0, exhibited exceptionally poor mechanical properties. This was attributed to inadequate contact between the silicon carbide nanoviscous and PP substrate, impeding the efficient heat transfer as depicted in the SEM image of P0 joint, which show voids throughout. In contrast, applying clamping pressure from P1 to P3 lead to noticeable increases in flexure strength and modulus of elasticity. However, these properties decline with higher clamping pressure at P4. Simultaneously, flexural strength exhibited a consistent decrease with increasing clamping pressure. Furthermore, the average thickness of the welded joint increased steadily with clamping pressure. This thickness increment correlated with enhanced silicon carbide nanoviscous PP substrate contact, facilitating deeper penetration of silicon carbide nanoviscous into the PP molten layer, and consequently, fracture strength and modulus of elasticity improve from P1 to P3. Beyond P3, however, fracture strength decreased, likely due to defects such as flashing and thinning at the welded joint, as in the photograph, leading to irregularities in the joint layer thickness, as you can see in the SEM image. In summary, optimizing clamping pressure is crucial for achieving robust welded joint layers with superior mechanical properties. As a summary, our results show that the optimal conditions for welding with silicon carbide nanoviscous suspension included an 18-second heating duration, 8.75 weight percent solid loading, 800 watt microwave power, and P3 clamping pressure. These conditions yielded the highest mechanical properties. Next, we investigated the use of silicon carbide nanoviscous PMMA nanocomposite thin film as susceptors in our welding process. Compared to susceptors suspensions, this thin film susceptor offers portability and ease of handling. By employing silicon carbide nanoviscous PMMA nanocomposite thin films, we aim to achieve homogeneous distribution of silicon carbide nanoviscous and uniform heating rate during the welding process, which is crucial for achieving consistent and reliable welded joints. This advancement represents a practical and efficient alternative to the traditional susceptor in the form of powder or suspension by simplifying the preparation process. The silicon carbide nanoviscous PMMA nanocomposite thin films was first fabricated using the solution casting method before being utilized as a susceptor. Similar to our study using the silicon carbide nanoviscous suspension, we investigated the effect of various parameters on the properties of the welded joint to identify the optimal parameters that give the best mechanical properties. In our investigation, we found that the effect of parameters on the microstructure and mechanical properties of welded joints are similar for both thin film and suspension susceptor. Notably, nanocomposite thin films require slightly longer microwave heating and higher solid loading of silicon carbide nanoviscous. Despite this, they achieve significantly superior mechanical properties compared to the suspension susceptor. SEM images confirm a more uniform distribution of silicon carbide nanoviscous in the welded joint layer. We achieved a tensile strength of 2.66 megapascal, modulus of elasticity of 1.65 gigapascal, and flexural strength of 12.28 megapascal by subjecting the sample to 800-watt microwave power for 50 seconds under P2 clamping pressure using a 40% silicon carbide nanoviscous PMMA nanocomposite thin film. And importantly, the thin film achieved 20% higher tensile strength than its suspension counterpart. Next, as we know, interfacial bonding is a critical consideration when dealing with materials of different natures. In our study, we utilized hydrophobic polypropylene as thermoplastic substrates and hydrophilic silicon carbide nanoviscous as the susceptor and filler to form composite welded joints. The inherent poor compatibility between the PP and the silicon carbide nanoviscous can lead to weak interfacial adhesion and hinder the full reinforcement potential of silicon carbide nanoviscous in the composite welded joint. To address these challenges, we perform surface modification of silicon carbide nanoviscous using silane coupling agents to improve the interfacial bonding between silicon carbide nanoviscous and PP and enhance the mechanical properties of the welded joints. In this study, KH570 and VTES were chosen for the surface modification of silicon carbide nanoviscous as they provide excellent compatibility with PP. This approach is expected to contribute significantly to achieving stronger and more durable welded joints with improved mechanical performance. This figure illustrates the mechanism of silane grafting onto the surface of silicon carbide nanoviscous. KH570 and VTS typically possess methoxy and ethoxy groups as their hydrolyzable components. During the surface modification process, these hydrolyzable groups react with water or alcohol, undergoing hydrolysis to produce silano groups. The OH groups of silicon carbide nanoviscous form hydrogen bond with the silano groups of KH570 and VTS. Simultaneously, the silanol groups also form hydrogen bonds with the neighboring silanol groups. Under water condensation, a silosane network or oligomer is formed, wherein the silicon carbide nanoviscous become covalently bonded to the silane coupling agent with the release of water molecules. After the grafting of KH570 and VTS onto the surface of silicon carbide nanoviscous, it is believed that the meta-acrylate group of the KH570 and the vinyl group of the VTS enhance the hydrophobicity of the silicon carbide nanoviscous. When these silane modified silicon carbide nanoviscous are embedded into the PP matrix during microwave welding process, the organofunctional groups are thought to form van der Waals bond and physical entanglements with the surrounding PP chains, and thereby further improving the interfacial bonding. The figure on the left illustrates the FTIR spectra comparison between unmodified silicon carbide nanoviscous and silane modified silicon carbide nanoviscous. Both KH570 and VTS modified silicon carbide nanoviscous exhibit peaks associated with SiO bonds, and peak correspond to CH2 groups in their FTIR spectra. The formation of the SiO bond is attributed to the reaction between hydroxyl groups on the unmodified silicon carbide nanoviscous and silanol groups from the silanes, facilitated by the water condensation. Additionally, KH570 modified silicon carbide nanoviscous display a peak indicative of the COO stretching vibration in the meta-acrylose group. Conversely, VTS modified silicon carbide nanoviscous exhibit peaks corresponding to CH double bond CH2 stretching and CH3 vibration in the vinyl group. The presence of these characteristic peaks confirm the successful grafting of KH570 and VTS onto the surface of silicon carbide nanoviscous. Figure on the right shows the water contact angle measurements of both unmodified and silane modified silicon carbide nanoviscous. Surface with water contact angle less than 90 degrees are typically considered hydrophilic, while those greater than 90 degrees are hydrophobic. Unmodified silicon carbide nanoviscous exhibited a water contact angle of 0 degree, confirming their hydrophilic nature due to the presence of abundant hydroxyl groups on their surface. Following surface modification with VTS and KH570, the water contact angles increased significantly, indicating enhanced hydrophobicity. This improvement results from the incorporation of the hydrophobic organofunctional groups of silane onto silicon carbide nanoviscous surface, which reduce the surface energy and promote water repellence. Moreover, we observe a dose-dependent increase in hydrophobicity. For example, 3% VTS modified silicon carbide nanoviscous show a water contact angle of 83 degrees, which is higher than the 75 degree for 1% VTS. Notably, KH570 modified silicon carbide nanoviscous exhibited higher water contact angle compared to VTS modified silicon carbide nanoviscous due to the stronger hydrophobic effect of the organofunctional group in KH570. In summary, these findings highlight that surface modification of silicon carbide nanoviscous with KH570 and VTS enhances hydrophobicity and confirms their potential to strengthen interfacial adhesion in composite materials. The left figures compares mechanical properties of welded joints using unmodified and silane modified silicon carbide nanoviscous suspension with varying KH570 and VTES percentages. We can see that the silane modified silicon carbide nanoviscous show improved properties due to enhanced dispersibility and compatibility with PP. It is noteworthy that adding 1 weight percent KH570 and VTES to silicon carbide nanoviscous improve mechanical properties, but at 3 weight percent, the properties decline due to reduced microwave absorption after silane grafting. Silane modification reduces the charge migration, significantly limiting dipole polarization and thereby lowering the dielectric constant of silicon carbide nanoviscous. Furthermore, KH570 modified silicon carbide nanoviscous yield higher mechanical properties than VTES modified silicon carbide nanoviscous due to the higher hydrophobicity of KH570 modified silicon carbide nanoviscous, as evidenced by the water contact angle results in the previous slide. Improved hydrophobicity enhances the compatibility between silicon carbide nanoviscous and PP, and thereby boosting the mechanical properties of the nanocomposite welded joint. The SEM image of the fracture surface of welded joint formed with unmodified and silane modified silicon carbide nanoviscous after single lab shear tests are shown on the right. The SEM images of the fracture surfaces shows gap and voids in the unmodified silicon carbide nanoviscous joints, indicating weak PP silicon carbide nanoviscous interactions. In contrast, the 1 weight percent KH570 and VTES modified joints exhibit rough fracture surface without gaps or voids, indicating improved interfacial bonding between the silane modified silicon carbide nanoviscous and PP matrix. However, you can see from the SEM images of the 3 weight percent silane modified joints where there are lots of unattached silicon carbide nanoviscous exhibiting incomplete embedding, result in lower mechanical properties of the welded joint. For silicon carbide nanoviscous PMMA nanocomposite thin films, we observe that the effect of surface modification of silicon carbide nanoviscous using silane coupling agents on the mechanical properties and microstructure of the welded joint is similar to those observed with suspension's counterpart. However, it is noteworthy that the mechanical properties of the welded joints formed using silicon carbide nanoviscous PMMA thin film as susceptors were significantly higher. For instance, the fracture strength of welded joints formed using 1 weight percent KH570 modifies silicon carbide nanoviscous PMMA nanocomposite thin film as susceptor was 3.19 megapascal, which is approximately 15% higher than the 2.83 megapascal observed for welded joints formed using the suspension's counterparts. This advantage arises from the use of nanocomposite thin films, which provide a uniform heating rate and homogeneous distribution of silicon carbide nanoviscous compared to silicon carbide nanoviscous suspensions. As a summary, surface modification of silicon carbide nanoviscous using silane coupling agents significantly improved the mechanical properties of both suspension and thin film forms. 1 weight percent KH570 modified silicon carbide nanoviscous show the best results, offering better compatibility and higher joint strength. Comparing to susceptors in the form of suspension, nanocomposite thin films provide a uniform heating rate and homogeneous distribution of silicon carbide nanoviscous, and therefore better mechanical properties. In conclusion, microwave welding utilizing silicon carbide nanoviscous as a susceptor, whether in suspension or thin film form, represents an effective and efficient method for joining thermoplastics. Susceptors in the form of suspension offers the advantage of easy application to components of any geometry without requiring additional processing steps, while susceptors in the form of nanocomposite thin films are portable and easy to handle. Surface modification further enhances the joint properties, resulting in stronger and more durable welds. This method holds great promise for industrial applications, offering a versatile approach to achieve reliable and high-performance joints in composite materials. I would like to acknowledge my team and the funding bodies that supported this research. Their contributions have been invaluable to the success of this project. Thank you for all your attentions. I'm happy to take any questions you may have. And I would like to take this opportunity to promote our journal, the International Journal of Nanoelectronics and Materials. We welcome your submissions and look forward to share your valuable research.